Let us start. So today we have a PhD seminar by Yuri Feldman. So a bit about Yuri. Yuri holds a BSc in computer science through the Technion, cum laude from 2010. And he has been pursuing PhD, direct track PhD in computer science since 2015. Go ahead.
So thank you. My PhD research is focuses on semantic perception for autonomous robots through viewpoint-dependent models. It was partially supported by an award of the Israeli Smart Transportation Research Center. So thanks for that support. So since the talk is about perception for autonomous robots, what's an autonomous robot? So an autonomous robot is one that acts autonomously, meaning without being directly controlled by a human operator. So say in comparison to something that is controlled directly, it has two key components. One is perception that provides understanding of the environment. For example, a map of the environment and robot state within it. And the second component is decision making, responsible for coming up with calculating actions, which would otherwise be provided by an operator. So in this illustration, environment provides, robot gets observations from the environment. The observations get processed by the perception into updated understanding or state estimates, which get passed to decision making, which outputs the next action to be done. So in this talk, we focus on the perception component, but we keep in mind the whole diagram in the sense that the environment representation, the state representation should be useful for, will be used in subsequent decision making. Of course, robotic perception needs to deal with uncertainty, which comes from noisy measurements, for example, odometry, aliasing, partial information, and imperfect models. We will touch on this later on. So yeah, briefly about semantic perception of semantics. So the question is, what does the environment representation need to include? And it depends. What it needs to include depends on the definition of the robot's task. So if the task is get from point A to point B, or map and vacuum the floor, then probably a geometric map saying where we can pass and where we can't, and where and an estimate where the robot is located within this map is enough. And this is this is addressed with there are established methods addressing it. The framework called simultaneous localization and mapping, because that's what it does. However, if the task is less structured, so say an autonomous vehicle drive down the streets from point A to point B, or for an household robot, go bring me a beer. So suddenly the robot needs to read the road signs and parse its whereabouts, well, the other things it's in its environment. The robot needs to understand that beers are usually found in the refrigerator, which is usually found in the kitchen. So it needs semantic information when the task is less structured. So semantic information is any information beyond geometric information that carries meaning. Coincidentally, deep learning methods allow semantic information to be more or less reliably extracted on a per frame basis. So given a frame, the robot should be more or less able to parse what's in the frame, usually. And so the question is how to represent, aggregate, and maintain this per frame information in a consistent and error resilient way. So This is what this talk is about. Okay, so we're talking about semantic perception, specifically viewpoint-dependent models for semantic perception. We will start with defining the semantic perception problem and what's a viewpoint-dependent measurement model, what we mean by viewpoint-dependent models. We will then proceed to describe 3 contributed approaches that address challenges in fusing semantic measurements, all making use of viewpoint-dependent models. And I'll note that one contribution that is underlying all those directions is that we're trying to jointly address the geometric and semantic aspects of perception under uncertainty. This is not what is usually done. The usual or the common assumption in works that address semantic fusion is that semantics are more precisely geometry is independent from semantics. We, on the other hand, take advantage of the idea of viewpoint-dependent models to couple semantics and geometry and come up with a unified, address them in a unified way. Okay, so first, so first, we briefly review the prevalent approach to localization and mapping, and define the notations that that we subsequently use. So suppose we have an autonomous agent, and say we want to calculate its pose over time in some global coordinate frame. We denote pose with x's, given a history of observations and user controls, sometimes also denoted with A as actions. So we can, so we simultaneously want to calculate its pose, its track, and build a map of its surroundings. So the common or a common approach is to formulate this as maximum a posteriori over robot track and some landmarks, points, 3D points that we can track, that we're able to track in the robot environment, and which are going to be our map. So this can be split using Markov property and Bias-law into a product of probabilistic factors corresponding to priors, motion model, and observation models. And if we choose the factors to be Gaussian, then this is a sparse nonlinear least squares problem, which we want to be able to solve iteratively. So at each time step, we update. We want to update our posterior with a motion model and motion factor and observation factors. And this can be done very efficiently thanks to sparsity, and for example described in these approaches. So this, what I described here, is called landmark SLAM. It's one of the 2 prevalent fundamental approaches, along with direct SLAM, and this one is closer to the approach to semantic perception we take. So just a note: a useful visualization for this problem is what is called a factor graph. It's a bipartite graph. It has variable nodes, one for each variable in the problem, and factor nodes, the black ones, one for each factor, and each factor node is connected to the nodes of all variables involved in the factors. For example, the motion model factors are connected to consecutive poses. Observation factors are connected to the observed landmark, and the pose it is observed from. We will be mentioning factor graphs again later. So we reviewed classical SLAM, and we now can proceed to define the semantic SLAM problem. So one formulation that became common is called object level SLAM, and the idea in it is to use static objects instead or in conjunction with geometric landmarks to map and navigate to the environment. So each object gets a variable O describing its geometry, which includes its 6DF pose, and a discrete class variable C that describes its class. So here C is a set of discrete class variables, one for each object, and same for O, it's a set of continuous vectors, one for each object. To be able to reason about the objects, the measurements are assumed to include object detections or equivalently segmentation with possibly noisy classification. And this is what we call the semantic measurement. So as before, we cast it as a maximum a posteriori problem over a robot track, classification and geometry of objects given history. But here the posterior, contrary to before, here the posterior is mixed, continuous and discrete, right? Because of the discrete categories. So we can develop this as we can split this into a product of continuous hypothesis weighted by the classification posterior given history. So the number of these hypotheses, we have one such hypothesis for each combination of classification of objects, and the number of this hypothesis is exponential in the number of objects, is the number of candidate classes to the power of the number of objects. Yeah, so as before, the continuous hypothesis can be split into a product of prior motion and observation model factors. This time, the observation factors are conditioned on object geometry and robot location when observing the object, as well as the object class, making it a semantic factor. And so each hypothesis, for each hypothesis, the set of semantic factors is different, corresponding to the combination of classifications. And this is reflected in the factor graph of the problem. Here we see that observation factors, which connect robot pose and the observed object, are switched by the class hypothesis. So for each class hypothesis, there's a different factor graph to be solved. And the semantic factor, as it appears here, predicts the measurement of an object of a given class when observed from a given robot pose. So if absolute pose information can be neglected, then we are left with a factor that depends on object class and relative viewpoint. So this is a viewpoint-dependent model. So since viewpoint-dependent models are a central part of this talk, so we'll review them a bit further. So a property of semantic measurements is that they are viewpoint-dependent. Classifier response varies with viewpoint, and an object may be misclassified from some viewpoints. And this property led us to consider viewpoint-dependent semantic measurement models. So for example, in this illustration, which is part of experimental results, which I will be presenting later, shows the spatial behavior of the classifier output for when input frames from various viewpoints. So here it is a mixture, the output of the classifier is a mixture between blue class and orange class. Some points are classified as rather blue and some as orange. So given a classifier output, the idea behind in viewpoint-dependent models is that given a classifier output, we can reason where spatially it was obtained from. And vice versa, given robot relative pose to object, we can reason if the classification vector we obtain matches the output expected from some given class. even if the classification itself does not make sense. So we can actually go further and model the spatial behavior of a general semantic feature vector, not necessarily class distribution, and which is why I tend to say that we treat semantic measurements rather than classification measurements. So the benefit of such models is that they allow to leverage the semantic viewpoint dependence for geometric inference, thus coupling geometry and semantics. A drawback is that since the model is conditioned on class, in practice, we need to learn a separate model for each class to operate. Semantic factor shows in the factor graph and as an observation factor connecting robot pose and the geometry, the pose of the observed object, and it depends on class. It is switched by the classification hypothesis. Okay, so this completes the introduction, and we proceed to describe the contributed approaches. So the first of which is an approach to object classification under uncertainty. So this approach was reported in ICRA and later extended to a Springer Autonomous Robots Journal article. So here is the semantic SLAM problem statement from before. It is split into a continuous hypothesis over geometry weighted by classification posterior. In this part of the research, we focus on this term, the classification posterior. We assume that the blue term was somehow already computed, for example, using just geometric SLAM. And in this context, we explore the way to address two challenging properties of semantic measurements. So this is what this part is about. So the first property is that semantic measurements are not independent. The images from close-by frames will yield similar classifier responses, which may be wrong or right. Whatever is the case, if we naively fuse it, ignoring the correlations, that means we just multiply the classifier responses, and we get an overconfident result. So we ignore the fact that since we took two frames from identical viewpoints, we don't get additional information. So a way that we can capture this idea is if we can come up with a model that provides a joint likelihood of classifier responses over a track of relative points, of relative poses for each for a given class. So the joint in the joint likelihood, we would be able to account for correlations. So one such model that allows this is Gaussian processes. So the assumption, the underlying assumption is that the classifications obtained from any set of relative poses are jointly Gaussian with some covariance function, and their joint distribution can be expressed conditioned on the training set. So we can fit a Gaussian process to training data for every object class, and then obtain this joint likelihood. Okay, so this is this addresses the part of so this would allow to address the part of correlation among views. So the second property of semantic measurements that we were aiming to address is the uncertainty of the model output that is due to difference between training and test data. So the thing here is this. So suppose a classifier was trained on fans that look like this. The question is, what will it output for this for a fan that looks like that? So we would like to classify, so it's not clear, right? Because it's significantly different. It's an extrapolation problem. We would like the classifier's output in principle to reflect the uncertainty. So we would like that no class will get a high score. So unfortunately, empirically, this is not the case. meaning that neural networks output tends to be unstable away from the training set. So we may actually get a very high score to an arbitrary class. This can be visualized with this illustration. So here in blue is the ground truth classifications we're trying to learn. In red are the training samples, the training set. The learned network output is constrained at the training set, and away from the samples, the uncertainty in which is pictured in yellow grows. And in practice, the network output becomes under constraint. By the way, there was a previous research in the lab done by Dima Kopikov that I think explored the reasons for that instability. It's called the neural spectrum alignment, I think. So thing is, turns out that this instability can actually be exploited to try to detect samples that are away from training set. This is an existing this approach was suggested by Galliarin and other publications around the time. So the idea is that we can look at multiple network outputs, slightly perturbing the weights, which yields, given a single input, yields a cloud of classifications. And the covariance of this cloud can characterize the uncertainty. So if it's spread out, then it means that a network is uncertain and the network output should be treated with care. If we formalize it, we say that to compute the posterior over class, the network output, we can, given the network training data, we can marginalize over the network weights. This posterior over network weights given network training data is called model uncertainty. It is not known and is heuristically defined by various methods. Essentially, all of them are network ensembles. Specifically, Galliarin's method, which is called Monte Carlo dropout, defines this posterior to be with dropping out weights during test time. So it's equivalent to multiplying the weights of the trained network with a set of Bernoulli variables. And this marginalization is then approximated with important sampling, meaning that we perform multiple forward passes and keep the resulting classification cloud, which characterizes the network uncertainty. Okay, so now we can with this we can develop a classification approach that accounts for correlation among viewpoints and for model uncertainty. I can't go into details here, but overall we assume that we have the current localization posterior, so we marginalize over it. Then we do a Bayes trick and some trick and arrive at an integral which involves both our joint class model accounting for correlations among time steps and involves model uncertainty. And turns out that this integral can be computed analytically because everything is Gaussian. Yeah, so this is the class model and model uncertainty. Okay, so I'll show some results. So we evaluated this approach in 3 settings: in synthetic simulation, 3D simulation in Unreal Engine, and with real world data from Big Bird and Active Vision, from Berkeley Big Bird and Active Vision dataset, which I will describe. So in all of the cases, we deal with single object classification from measurements obtained over a track. Localization of the robot is uncertain, but an estimate is available. So the criteria that appear in the plots are probability of ground truth class, naturally higher is better, and another criteria we called it most likely to ground truth ratio. So it's the ratio between the most likely class and the ground truth class. So if the ground truth score is low and the most likely score is high, this will be large. So lower is better, and this measure is sensitive to confident misclassifications. And we compare our approach with a model-based approach, which uses GPs for classification, but does not deal with localization uncertainty, and with naive-based approach, which just directly fuses class predictions, directly fuses classifier output. Okay, so for the synthetic simulation, the presented plots will show statistics for several hand-specified scenarios, where statistics collected over realizations of simulated classification. Classifier outputs. Classifier outputs measurements come from ground truth Gaussian process, and Gaussian processes for candidate classes are just hand specified. So there are 3 candidate classes. For each, there is a hand specified process modeling the output. We have 2 kinds in all our settings. Actually, we have 2 kinds of scenarios. One is a benchmark of model uncertainty. In the case of synthetic simulation, the simulated to simulate model uncertainty, wrong classifier output, we take the simulated classification and randomly offset it. And our method is input with the uncertainty with a standard deviation. And the second benchmark is localization uncertainty, where we do the same for localization. So classification, we don't touch classification, but we bias localization in a way that creates aliasing between classes. I will show this, and we input our method with the uncertainty, this covariance of the localization error. So for the model uncertainty, here are plots for the model uncertainty benchmark. So in each of the plots, the color patches are 10% percentile steps. In the middle, the saturated line in the middle is median of each method, and the percent of steps, the percentage here is the percentage of time steps with ground truth class being the most likely. So in red is naive Bayes. In blue is our method. So left column is most likely class, and right column is this most likely to ground truth ratio. So we can see that the naive Bayes, the top row, we can see that it was arbitrarily. We can have it arbitrarily off because of the erroneous, because it directly uses classifier output, so it's erroneous input. And in green, model-based generally gives high scores to the ground truth. The probability of correct class is generally high, but nearly, if we look at the percentiles, nearly 30% of the cases misclassified. In nearly 30% of the realizations. I mean, at the last time step after fusing all the measurements. So in contrast, our method can be seen to accumulate information because it is input with the uncertainty. It uses compensates for the uncertainty. For the synthetic localization uncertainty scenario, what we did, we introduced a specific localization bias, which makes an incorrect, which makes the classification measurements more similar to an incorrect class. So model-based picks up the wrong class. Model-based is fooled by that. Naive-based is naturally unaffected by that because it is not affected by localization. It doesn't use localization. We would be affected by that, but because we are input, we account for the localization uncertainty, we are able to gracefully accumulate information. These results we replicated it across essentially across the three settings. So I will not go into the 3D simulation, but I will talk a bit about I will show the real the results for real data because we use this data set again subsequently. So the evaluation on real data consists of actually two data sets. One is big Berkeley instance recognition data set, which has data for 125 objects taken from this dome-shaped from poses located on a dome. So object is placed on this rotating table, and there are those 5 cameras that capture 120 views. And then there is, in conjunction with this dataset, there's active vision dataset, which has photos from apartment, localized views of from a set of apartments. I think it says a few dozen apartments. Which contain those objects from the Big Bird dataset, which contain detections of those objects. So we used the Big Bird dataset to learn the GP models, and then we used those GP models to classify. We specified a scenario in the active vision dataset. We took a subset of views and used the learned GP models to classify this subset of views. Again, we did the localization uncertainty experiment. So we exactly as in the synthetic case, we noised the localization, and we again see that this makes the model-based method fail because it does not account for the localization uncertainty, whereas our method does account for localization uncertainty and performs correctly. A model-based method, I'll specify, it is generally it generally outputs high confidence results. So it usually correctly outputs the correct class as most likely, but in some 15% of example, it just fails. It outputs the probability as 0, essentially. We correctly classify in all cases because we account for the uncertainty. And this is examples of images of objects from this Big Bird dataset and the learned GP models. So this was the first direction. So we now proceed to the second contribution, which is a scheme for data association aware semantic slum. Attribution disclaimer: this part of the research was done in collaboration with Vova Chuyev and was published as an IRIS paper. We did the theoretical development together, and I contributed to the paper, but the implementation and the experimental results that I present are entirely Vova's. In this part of the research, we aim to relax the assumption that we were making implicitly until now of known data association. That is, until now we assumed that we know somehow which object produced every measurement, and in practice it may not be easily resolvable due to aliasing. So, for example, in the illustration, suppose that the robot knows that it should see two chairs. So the scene should contain two chairs, and it gets two detections, both of which are classified as chairs, but no further information as to which is which. So if the robot associates correctly the left detection with the red chair and the right one with the white chair, then it calculates that its position is here. If, however, it picks up the reverse association, then actually it calculates its position to be there. And in practice, both hypotheses have to be considered valid until disambiguation information arrives, because they're equivalent in absence of disambiguation information. And the same situation can happen when a robot revisits a location during a loop closure. So if the robot, if we make a hard, irreversible wrong decision on data association, then we will probably completely ruin the estimate. Okay, so let's add data association variables marked as beta, a discrete variable per observation, holding the index of the object which generated the observation. And again, we can split the posterior into a continuous hypothesis over geometry and the hypothesis weight. And this time, the number of hypotheses is the number of classification combinations as before, but multiplied by number of objects to the power of number of time steps. So this is huge and completely intractable in theory. So yet the advantage of objects is that they can often be detected across viewpoints, and in fact there is much fewer of them than landmarks. So they actually allow the probabilistic approach to data associations that we take, which would be completely impractical with landmarks in principle. So our contributions are first that we show that in practice the above approach is tractable, since most hypotheses have negligible weights and can be pruned away, while maintaining plausible hypotheses until disambiguation. We show that the viewpoint-dependent model aids data association, aids reduce the number of valid hypotheses. And again, this approach as well operates with general semantic feature vectors, opposed to baselines that usually take just most likely class. So the approach boils down to this. We denote the continuous hypothesis associated with a given combination of classes and data association as belief over a robot track and object geometry given classification and associations, and denote the corresponding hypothesis weight as W. Then on every time step, we receive a user action. So here it is defined as A, what is previously user defined as controls with U, and observation. So to propagate the belief, we take the belief of the hypothesis in previous time step, we replicate it for each combination of classification and association of the new observation, and we update it with a motion model and with the observation model corresponding to the current data association and classification hypothesis. And we set the weight of the hypothesis proportional to the weight from last time step multiplied by association probability. This is a probability that the current detection originated from this object, from the object in question. So we take this association probability and average it over the geometric belief, propagated belief. In the experiments, in practice, we just use this as a binary line of sight indicator. ignoring, for example, other objects. But in principle, this could be elaborated to reason about occlusions and other complexity. And finally, after weights, updated weights that fall below a threshold are pruned, meaning their hypotheses are discarded to keep the number of hypotheses tractable. So this is the approach. And the experimental results are in a simulated environment with so we had a simulated environment with 6 identical objects and 2 candidate classes, and the number of classification hypotheses was 64 maximum classification hypotheses, and an informative robot pose prior, so the robot doesn't know where it is. So after one time step, so we compare without using a classifier model and with using classifier model. The candidate classes have synthetic classified, hand-specified classified models. So the results here are from the first, after the updating with the first measurement. On the left, when not using the classifier model, significantly more different hypotheses than on the right. And towards the end of the track, the same scenario towards the end of the track, when not using the classifier model, the method was still not able to disambiguate the position. When using the classifier model, it was able to disambiguate and also calculated more precisely. The estimate is more precise. So this is another view of the same thing. This is a distribution of the weights. So we see that the red distribution is more in green is the correct hypothesis, and we see that the red distribution is much higher, much more confident in the correct hypothesis. So we get stronger disambiguation when using the viewpoint-dependent, stronger disambiguation and more precise estimates when using the classifier, the viewpoint-dependent model. This is what we got here. And in practice, the number of the overall number of hypotheses remained tractable. So we were way under the theoretical maximum number of hypotheses in this simple scenario. Okay, so this was the second contribution. So we now proceed to the third direction, which is a novel approach to semantic SLAM, which is based on continuous inference over a learned representation. So we note that the semantic SLAM problem, which we defined, the problem with this problem that we defined can be identified as using discrete object categories. Right, so using discrete categories renders this a mixed inference problem and means that we are forced to maintain hypothesis if we want to solve it precisely, and it also means that it also requires, in our approach, it requires learning pair class models. And another limitation is that it imposes granularity, granularity on the semantic representation. So from the previous example with the chairs, we had a real problem with that. We had the chair class, and as soon as we got a detection and a classification and discarded the frames they were coming from, we lost the ability to distinguish between those two very different chairs, which was detrimental to ability to disambiguate data that association. So alternatively, we could try to add more granularity, but as soon as we add, meaning more classes, as soon as we add more classes, then we increase the complexity and the number of possible hypotheses. If worse, we want to add more semantic discrete properties, for example, discrete color variable, then the complexity, the number of hypotheses immediately increases exponentially. There's a real representation challenge here. The idea, so there's an idea, since the problems are caused by the discrete variables, what if we could somehow replace them with the pair object discrete classification with a pair object continuous representation vector? If we do that, suppose we can do that, then we would be dealing with a continuous inference problem, right, which we know how to solve efficiently. And here's the corresponding factor graph. So for each object, it contains a continuous geometric description variable and a continuous semantic description vector. In fact, these are separate nodes in principle. And the semantic description vectors reside in some space in which ideally each point corresponds to some object. And the semantic perception problem becomes then inference inside this semantic representation space, where given multiple measurements of an object, we want to infer its corresponding semantic representation vector. Okay, so yeah, there's a bit of a mess, but explicitly in inference, in this case, we maintain a joint posterior over robot track, object geometry, and per object continuous semantic representation vector. If we again split it recursively, we obtained at time step k, we obtained the belief from previous time updated with the motion model and the semantic observation model. And then the approach boils down to coming up with this semantic observation model. So we can see that immediately the advantages of this approach. That first, we need a single, there's a single continuous semantic observation model. We don't need to learn pair class models. This is continuous inference, which can be done. There are efficient approaches to solve. There's no discretization on semantic representation. So there's this idea that semantic representation space is continuous. So how to fit this kind of model? So our one of the initial approaches, an initial approach is first we take this observation model and we discard previous time steps. We just leave the relative pose and the semantic description vector. So this is a viewpoint-dependent model, and we model it as a Gaussian over the image obtained the current time with mean specified with learned mean, with mean modeled by a neural network. And we used in practice constant diagonal covariance. In principle, not only constant and not only diagonal covariance can be used, but it was a simplification. So the cost function for the objective function for learning this model can be specified as maximizing this posterior over joint posterior over frames images and semantic representation. Given, say, we have data from like a Big Bird dataset, so we have frames of object detection with corresponding relative poses. So we can calculate this posterior over these detections and the representation vectors of the corresponding objects, given the relative poses and the associations, naturally. And this is equivalent to this taking a log. This is equivalent to this problem of optimizing a log sum of this viewpoint-dependent observation of likelihood specified. This is our viewpoint-dependent observation model we are trying to learn, plus some prior on the representation vectors. In practice, we use a contrastive prior to have them as independent as possible. And note that in principle this can be used even okay, so I'll note this. This can be used even online. So assuming that we can count on the relative poses, on robot poses, say we get from mockup or somewhere this information, then we can collect this data online. We don't need a very controlled setting. So the results here are some results from fitting in this example frames. Middle is the learned semantic TSNE representation of this learned semantic space and the distribution of the corresponding object detections. Here, this model predicts frames from given relative viewpoint and relative embedding. So here is the mean predictions of this model. On the right, that's a visualization when we took some frame and we took the corresponding representation vector corresponding to the object and played around with the relative pose. So we can see that the model picked up nicely the viewpoint dependence. And we were able to show inference with this model. So in black here, in black, one line is initialization, and in blue is the estimate using this model. So we can see that the resulting on the right plot, the colors are different. So the estimate errors are in green, actually the final estimate error. So we can see that we reduced significantly the initialization errors. There's just one problem with this approach, is that it doesn't generally work. So this is a cherry picked. So we were able to demonstrate inference, but generally it did not work. The fundamental didn't work. We identified the fundamental reason with that maximum likelihood does not provide sufficient gradients. So the thing is, the cost function only constrains the values at training examples, whereas when we try to use the learned model for inference, we actually have wrong initialization. So we're not on training data, we're away from training data. We have wrong initialization for the variables, for the relative pose and the object descriptions, and we try to converge back to the ground truth. And this nothing provides. Maximum likelihood does not provide that. It does not constrain the model away from the ground truth. So just a visualization of what I mean here. The plots here are plot this values of the likelihood around the ground truth point. So at 0, 0, that's the ground truth. In each plot is the ground truth. And the axes are offset with respect to the values of the variables, 2 axes at the time of the variables. So in principle, the maximum likelihood should be at 0, 0. It's not always at 0, 0, which may be related to model expressiveness. But ideally, it's at 0, 0 at the ground truth point. And if we start, like in the right plot, if we start, x is the initialization point. If we start from a noise estimate, we would like to be able to converge closer to the ground truth. We would like to improve our estimate. And this isn't provided by the maximum likelihood because we don't get, in this case, it is provided, but in many other cases it is not, because optimization just gets stuck. So we don't have sufficient gradients to converge. And another problem in this initial formulation is that the factor is huge because we're predicting the whole frames. So it means that the Jacobian is around 1,000 by 20. It's a huge Jacobian. I'll just briefly mention it. I realized that my time is nearly over. So the thing is, say we're trying to learn this model, which is this surface. The training set constraints this model. Training set consists conceptually of triplets: relative pose, ground truth representation, and a frame obtained. And it constrains the model at a sparse set of these triplets. And we want to try to improve inference by shaping the model in between those triplets. So we formulated another approach for that. First, we used the feature extractor. So we model features instead, reducing the dimension of frames to, in practice, 12. That's what I used in experiments, keeping the rest of the model the same. The main change was in the cost function. So first we added the regularization also on the feature extractor. Will not go into it. The main point here is the new data term, which we used the following one. So the data term for training example I is the expectation over offsets with respect, small offsets with respect to the training example of the value of the offset. It's a vector, the offset vector, plus the optimization, the step that optimization would do for this offset, for this training example. So ideally, we would like this sum to be 0, right? Because we would like the optimization to compensate this offset, and we normalize this value by the size of the offset. Okay, so for gradient descent, for example, this optimization step is equal to minus the gradient of the model at this offset. So our data term directly constrains gradients in around each training example to point towards the ground truth principle. This value itself is interesting because it can be viewed as the ratio of the distance to ground truth after taking the optimization step to the initial. That is, by how much, multiplicative factor, by how much did we improve after one step our estimate. Okay, so I see that my time is really up. So in this approach, we were able to get useful gradients and inference, and still doing experiment with it and inference in a scenario. Okay, so that concludes it. I'll just note that there are a few other this kind of approaches started to receive interest, but other approaches which we saw until now did not constrain, did not have this expectation. So they did not come up with random poses. They constrained only they constrain the gradients only on optimization steps. So we think that this approach is more efficient and is different than what is proposed. After coming up with this, we discovered that others tried also constraining the gradients, but in other ways and in other contexts. So this was not used for semantic slump; it was used for other things. Okay, so in summary. So we addressed semantic perception under uncertainty using viewpoint-dependent models, and we went through 3 novel approaches to address semantic perception That's we showed that our approaches are resilient to uncertainty, and the final approach, which hopefully we'll be able to publish, may allow semantic perception to be much more widely applicable, because it requires both requires less training data, and it's more efficient than the other approaches.
Okay. Thanks, Yuri. Thanks so much. We have time for one quick question before concluding. If anybody wants to ask briefly, now's the time. Right. Otherwise, thanks again, Yuri, and thanks again, and see you next time. Thanks.